Hi everyone, welcome to my video. Today we're gonna speak about visual inertial estimation of velocity for multicopters based on vision motion constraint. So what is a multicopter? A multicopter is a mechanical simple aerial vehicle whose motion is controlled by speeding or slowing down multiple thrusting motors or propeller units. Multicopters are aerodynamically unstable and absolutely require an onboard computer to have a stable flight. A copter can control its roll and pitch, rotating the speed up to two motors on one side and slowing down the other two. So, for example, if the copter wants to roll left, it would speed up the motors on the right side of the frame and slow down the two on the left. Similarly, if it wants to rotate forward, it speeds up the back two motors and slow down the one on the frames. So it can go left or right by speeding up two motors on the diagonal across from each other. The horizontal motion is accomplished by temporarily speeding up and slowing down some motors so that the vehicle is leaning in the direction of the desired travel, increasing the overall thrust of the motor. So the vehicle shoots forward. Generally, the more the vehicle leans faster, it travels faster. So why we need this? Like in the recent years, this unmanned vehicle has been the main attraction. They've been using it for search and rescue, load transportation, aerial manipulation, surveillance, and agricultural application. However, there exist some scientific and technological challenges. Velocity estimation is essential for multicopters to guarantee flight stability and maneuverability. Such velocity estimation based on visual and inertial information in GPS denied or confined environment. In this method, there's no map, artificial landmark of the environment is required, and only the offset shelf onboard sensors in the multicopters, including low cost inertial measurement unit and download looking monocular camera and an ultrasonic rangefinder, are exploited to constitute the vision motion constraint. This constraints conducts metric velocity with the point correspondence between the successive image, in which an efficient approach based on mean shift algorithm is developed to detect the outliers and select the optimal matching points. So as you can see, there are three coordinates frames defined in this estimation system: Earth fixed coordinate frame, which is called EFCF, aircraft body coordinate frame, which is called ABCF, and the camera coordinate frame, which is CCF. With the coordinates of origin, which is OE, located on the ground plane or the initial position where the multicopter takes off. Since the ground plane is assumed to be horizontal, the plane coincides with the ground plane. And the third component of any ground point remains 0. The ABCF, which is B, is 0BXB, YBZB is the ground plane. And the center of the gravity of the multicopter is chosen as the origin OB from frame B. The IMU model are mounted in the center of gravity of the multicopter, and the measurements of the IMU are with respect to frame B. A monocular camera is attached to the bottom of the multicopter in the downward looking direction with a small offset of the center of gravity. We use RB raised to C and TOB raised to C to describe the rotation of translation from frame B to frame C, which can be calibrated in advance. So how we analyze these monocular vision measurements? Like, the onboard monocular camera is looking downwards to capture the images of the ground scene. There exists a vision motion constraint between matching features of two successive images. As you can see, the delta t as sampling in time interval at tk and tk minus 1 is equal to tk minus delta t can be current and the last sampling time instant, respectively, given two images captured at the same time, that is tk and tk minus 1. The correspondence rotation matrix is from frame B to frame E, and height information are denoted as RK and HK, which is greater than 0, and RK minus 1 and HK minus 1, which is greater than 0 as well. So the center of gravity of the multicopter in the EFCF as tk and tk minus 1 is expressed in two successive images. So what about this mean shift algorithm, which is MS algorithm in short? Like, MS algorithm is a simple non-parametric iterative technique for estimating density gradient, which was proposed by Fukunaga in 1975. After 20 years, the MS algorithm became popular with successful application ranging from image segmentation to object tracking and clustering. It is a stable, iterative method to locate the maxima of a local density function or given a collection of discretely sampled data. Given sample data in the d-dimensional space, which is r raised to d, the multivariate kernel density estimate with only search window of radius r computed in the point epsilon in r raised to d, where c, r, and d is a normalized constant, then the gradient of the kernel density estimation is established like this. When the gradient of the kernel density estimate equals 0, that is when the epsilon star is maxima of the estimated probability density function regardless of the constants c, r, and d. Furthermore, for iterative operation, the MS algorithm starts from one of the data points and iteratively update the location of the points until a maxima, namely the optimal value, is reached. It should be noted that there is a sufficient condition for convergence of MS algorithm to guarantee the existence of maxima. The conclusion and corresponding proof and summarized when the mean shift is small enough, that is yj modulus of yj minus 1 is less than epsilon. Precision epsilon is set to 0.01. As you can see, that solid black line indicates the number of inlier detected without using the MS algorithm, while the other curve shows the results after the process of MS algorithm. It shows that some outliers are detected and rejected with the bandwidth controlling the searching range. When the bandwidth is small, example the r is equal to 0.5, almost all the points are identified as outliers, resulting in few inliers detected. The number of inliers detected becomes greater with the bandwidth increasing. However, if the bandwidth is chosen as large as 0.5, the number of inliers detected almost remains unchanged and the MS algorithm takes little effect. Thus, the bandwidth value is selected 0.3. So, this visual inertial method based on vision motion constraint provides accuracy, velocity information, merging the measurement from a monocular camera and an IMU and an ultrasonic rangefinder combined with a unique multicopter dynamic model. An efficient approach based on MS algorithm was developed to detect the outliers and selected the optimal match points between the successive images. Observability and analysis has shown that the proposed estimation system is observable with at least one feature corresponding detected with the multicopter in hovering condition or steady flight. Comprehensive simulation experimental result has verified the process estimation method works well in GPS defined or confined environment with a good texture of inner features. In all the methods, all we need is the onboard sensing without the aid of external localization system, any artificial features or any prior knowledge of the environment. Furthermore, the proposed method is valid with only one matching point detected. Even for the worst case, without any features detected it will affect during a short interval. However, there exists some limitations in this estimation. A flat, which is strong assumption, it is also observed that the proposed method takes effect at low altitude and slow velocity. Measurement delays are ignored for simplicity in our method. We assume that the system is nearly linear. If it's non-linear, we choose the altitude as the known as unknown state. So thanks for watching this video. I hope you enjoyed it and see you.